talking about NASA's technologies for direct imaging temperate terrestrial exoplanets from space. Very interested in this one.
All right, thanks, Kim. So how's my audio? Can you hear me okay?
Yeah, I can hear you just fine.
Excellent. Okay, well, thank you so much for having me here today. So my name is Brendan Crill. I work in NASA's Exoplanet Exploration Program, which is located here in Southern California, normally at the Jet Propulsion Laboratory, now kind of locally dispersed, of course. So what is the NASA Exoplanet Exploration Program? Well, we're a program office of the NASA Astrophysics Division. Kind of broadly, you can think of us as the arm of NASA when it comes to all things exoplanet related, and we undertake a really wide variety of activities. Another important function we serve is kind of the connection between the science and technology community that we serve, that's us here, and NASA headquarters. So we do quite a bit. I'm going to focus on what we do to develop technology for NASA's future exoplanet missions. And so the motivation for this, and in fact, how we set our priorities and what technology to work on, come from the 2010 Decadal Survey. So this is the process that happens every 10 years that sets the nation's science priorities, and agencies such as NASA and NSF follow those recommendations. So 2020 is underway now, but we're still acting on the 2010 recommendations. And they recommended in the area of exoplanets what they called the New Worlds Technology Development Program, which was to develop technology that would enable NASA to carry out a planet direct imaging mission. And actually, it's not in this table, but if you read the actual text, the focus is really on terrestrial exoplanets, so kind of Earth-like, orbiting sun-like stars. And the Decadal recommended we spend 100 to 200 million over 10 years, and we've been doing that. 2010 is getting a little stale now. It was a totally different world back then. But the direction we're going in, I think, was reaffirmed by another study that the National Academies undertook a couple of years ago called the Exoplanet Science Strategy. And their top recommendation, in fact, went a little further than what the 2010 Decadal Survey said. It said NASA should actually develop a very large mission with the science goal of being able to take reflected light spectra of terrestrial planets. So that speaks to, on one hand, that our technology has been proceeding in the right direction and kind of reaffirms this goal. So this is the series of NASA-led exoplanet missions, past and present and near future. We're in the era of TESS today, and looking forward to the kind of amazing science that James Webb will bring when it launches. Beyond that, there's another large flagship astrophysics mission, the Roman Space Telescope, which is under development. And in addition to carrying out a microlensing survey, from a technology standpoint, Roman is extremely interesting because it's including a coronagraph instrument. It's not the first coronagraph to fly in space, but it's the first one that has an adaptive optics system with a deformable mirror that will enable very deep contrast. So that's a big step along this direction towards being able to image Earth-like exoplanets in their habitable zones. Beyond that, the future is somewhat hazy, just like the air outside in Pasadena. And anything beyond Roman will depend on the outcome of the ongoing Decadal Survey. But there's a number of missions that have been considered, and the Decadal Survey will weigh in and make its recommendations, but some possibilities that we've been working towards are a Starshade rendezvous mission that would join Roman late in the 2020s and enable very deep, 10 to the minus 10 contrast direct imaging. Beyond that, you probably are familiar with the mission concept studies called LUVOIR and HABEX, which recently wrapped up their final reports about a year ago. Both of these were designed with the goal of detecting Earth-like exoplanets. They both were designed around very high contrast coronagraphs that would enable that. HabEx also included Starshade technology as well. So these kind of represent the kind of range of missions that the technology we're working on now might enable. Another mission under consideration that's very important, and we're in fact funding some technology development towards, is the Origin Space Telescope, which would go even further than James Webb's capability at transit spectroscopy in the mid-infrared. And then even beyond that, we're not working on the technology now, but we kind of have in the back of our minds the possibility that very long term, we might need to be thinking about technology for interferometers. So the kind of key technology that's needed for something like a LUVOIR or HabEx that could directly image a Earth-like exoplanet is really in the starlight suppression. And there's kind of two architectures that are under consideration based around, you can base your architecture around a coronagraph, which suppresses the starlight internal to the space telescope, or around a Starshade, which has a free-flying spacecraft that blocks the on-axis starlight as well. So those are kind of the main areas in which we're working on technology for. Of course, another way you could suppress starlight that's come up in some really exciting talks. There's a lot of really cool work being done on the ground in this regard. Nulling interferometry could also serve this function. But at the current time, NASA has decided specifically to put investment in that for space missions off into the future. So really we're focusing on these two types of architectures. So how well do we need to do? So this is a very nice plot put together by the Project Science team of the coronagraph instrument for the Roman Space Telescope, showing the phase space of brightness contrast, the ratio and brightness of the planet to the star, versus angular separation. And Earth at 10 parsecs is down here in the lower left. So that's kind of the performance that we're aiming for. The present day achieved performance is up here in the upper left. The red squares here are the known directly imaged exoplanets. As you know, we've heard about them during this conference, of course. They're not really anything like an exo-Earth. These are the self-luminous, hot Jupiter, very young planets detected in the infrared. And you can see these curves showing the performance of existing instruments on the coronagraphs on Hubble, ground-based coronagraphs, and what's expected with the James Webb coronagraph, which actually has a coronagraph on board. They're not high contrast one. So we're up here, and the coronagraph instrument on Roman is going to kind of split the difference, get us into the 10 to the minus 9 to 10 to the minus 8 range, and close in on that angular separation with its 2.4 meter telescope. So even though there's work to be done after Roman, it gets us quite a bit of the way there. So what I showed you on the last page showed a gap in the performance between what's been currently demonstrated and achieved and where we need to go. We break that down further in terms of specific technology gaps and to figure out where we need to make investments. So the areas we need for a coronagraph to achieve the necessary performance on a telescope are contrast. It has to get to the level necessary, has to be stable over the period of time it takes to image a Mag 30 source, such as an exo-Earth. Every photon becomes precious at that, for those very faint sources. So detectors are important to invest in. And then large space telescopes are also needed to push that angular resolution closer in and be able to survey more habitable zones. So these are the kinds of technologies that we're investing in different ways to try to close these gaps. On the Starshade side, we have, there's different gaps. The starlight suppression function is carried out by this free-flying telescope, but that has to be validated somehow. The free-flying structure has to be aligned properly with the space telescope. And also this very large structure has to be deployed to fairly good precision from a stowed state that so it can fit inside a rocket launch fairing. So that this is kind of all the work that's being done. And actually, I'll just mention that at least for the case of something like a rendezvous with the Roman Space Telescope, the formation sensing problem has actually, we think, been closed. And so we're not really working incredibly actively on that one anymore. Okay, so now I'm going to just give you in the remaining time a very quick overview of these activities and then point you to where you can find out more. So these are the activities we undertake to try to close these gaps. So with our colleagues in the other astrophysics program office, we track the technology gaps, some of which I presented to you a minute ago. And we update those every 2 years now. We produce a report that you can find online. There's a program that many of you are probably familiar with called the Strategic Astrophysics Technology Program. This is a competed pot of money to develop specific technologies. A lot of this has gone into the areas shown here. A lot of coronagraph work, great advancements in coronagraphs have come out of this program. We manage on behalf of NASA a facility that we call the High Contrast Imaging Testbed that actually allows, it's open to any principal investigator of a Strategic Astrophysics Technology Award. It's a facility located at JPL that consists of a large vacuum chamber and a ultra stable test bed to try to basically give you the conditions that a space coronagraph would be operating under. And so this is a facility that it's kind of a common user facility. You can kind of think of it as an observatory. We recently upgraded this with a really nice wavefront sensor that's been shown to be able to measure on the time scale, that's been able to measure wavefront errors on the scales of better than a picometer, which is pretty amazing. And that's very useful for these PIs to evaluate the performance of their instruments and demonstrations. We support the CGI mission, not directly, but we actually manage the test beds that they use to develop their technology. So we're keeping a close eye on them, given how important they are to us. We carry out some studies, some design studies. A few years ago, it wasn't even known if a coronagraph could achieve the necessary performance behind a segmented telescope. So we've gathered a bunch of people together to try to address those questions. We manage the Starshade technology development effort that's done on behalf of NASA Astrophysics Division. And then we have a couple of other initiatives underway right now, things that kind of come up from time to time that we feel need to be pushed forward. So we're looking into, we're carrying out what we're calling a deformable mirror survey. We're making sure we're aware of all the options for deformable mirrors that could be used in space. And then many of you are probably aware of this report that came out recently on the necessary steps to achieve radial velocity sensitivity that would be able to measure the Earth down to Earth masses from the ground. And that actually came out of the Exoplanet science strategy. And we're helping to respond to that. There's actually a opportunity out there now that we're looking forward to funding some proposers to help address those. So, you know, hopefully I've given you the sense that we're doing a lot of different things in a lot of different areas. To find out more, to dig in a little more detail than I had time for today, please go to our website. You'll find details on our gap lists, on all of the active and past Strategic Astrophysics Technology Awards. We carry out kind of on an ad hoc basis, usually happens every couple of months, a colloquium series online. And you can find the talk recordings there and actually contact me if you're interested in getting on the distribution list for those talks. You can find out what our technology, our segmented coronagraph design and analysis study has come up with. And then I'd like to invite you to contact me with any other questions you might have. And thank you very much. I'm not sure if we have time for questions now, but I'll stick around in the Slack and answer whatever folks need to, would like to find out about. Thank you.
All right. Yeah. Thank you very much, Brendan. I don't think we do have time for questions, but that was a great talk. Thank you very much.